You're listening to LeadAI.dev, your daily updates on AI development. Today's topic is GitHub's eBPF deployment safety system prevents circular dependencies. Here's a quick overview. GitHub's innovative eBPF implementation automatically detects and prevents circular dependencies during deployments, reducing system failures by up to 90% through real-time monitoring. Now, let's ask our analyst about these developments. What's new? GitHub's eBPF deployment safety system for circular dependency detection?
GitHub has implemented an advanced eBPF based system that automatically detects and prevents circular dependencies during deployment processes. This system monitors deployment tooling in real time, identifying potential dependency loops before they can cause system failures. The implementation leverages eBPF's kernel level visibility to track service interactions and dependency chains across GitHub's massive infrastructure. The system has already prevented hundreds of deployment failures that could have impacted millions of developers worldwide. The technical implementation uses custom eBPF programs that attach to kernel trace points and network events to monitor service communication patterns. These programs collect dependency metadata during deployment operations, building real-time dependency graphs that are analyzed for circular references. The system operates with minimal performance overhead, adding less than 2% latency to deployment operations while providing comprehensive visibility into service interactions. GitHub's engineering team developed specialized algorithms that can detect complex multi-hop circular dependencies that traditional static analysis tools often miss. Before this eBPF implementation, GitHub relied on static dependency analysis and manual code reviews to prevent circular dependencies. The previous approach required developers to manually trace dependency chains and often failed to catch runtime circular dependencies that emerged during actual deployment scenarios. The new system represents a shift from reactive to proactive dependency management, catching issues at the kernel level before they propagate through the deployment pipeline. This advancement reduces deployment rollback incidents by approximately 85% compared to the previous static analysis approach. Real-time circular dependency detection with sub-millisecond response times using kernel-level eBPF monitoring automated dependency graph construction that tracks service interactions across distributed deployment environments, integration with GitHub's existing deployment toolchain including actions, workflows, and container orchestration systems, prevention of complex multi-hop circular dependencies that span multiple services and deployment stages, performance overhead limited to 2% additional latency while providing comprehensive deployment safety coverage.
Thank you for that analysis. Let's move on. Who benefits from GitHub's eBPF deployment safety implementation?
Platform engineering teams managing complex microservices architectures gain the most immediate value from this eBPF deployment safety approach. Teams deploying more than 50 services simultaneously see significant reduction in deployment failures and rollback incidents. DevOps engineers working with containerized applications and Kubernetes clusters benefit from the real-time dependency visibility, especially when managing service mesh deployments. Organizations with frequent deployment cycles multiple times per day experience substantial improvements in deployment reliability and reduced incident response times. Secondary beneficiaries include development teams working on distributed systems where service dependencies change frequently during feature development. QA teams benefit from more predictable deployment outcomes during testing phases, reducing environment instability issues. Site reliability engineers gain better observability into deployment time dependency issues, enabling faster root cause analysis when problems do occur. Security teams also benefit from the enhanced visibility into service communication patterns during deployment processes. Teams with simple monolithic applications or those deploying fewer than 10 services may not see immediate value from implementing this level of dependency monitoring. Organizations with well-established static dependency analysis processes and infrequent deployment schedules might find the implementation overhead outweighs the benefits. Small development teams without dedicated DevOps resources should consider simpler dependency management solutions before adopting eBPF-based approaches. Platform teams managing 50-plus microservices with complex interdependencies and frequent deployment cycles, DevOps engineers working with Kubernetes, service mesh, and container orchestration platforms requiring real-time monitoring, SRE teams needing enhanced observability for faster incident response and deployment troubleshooting, development teams building distributed systems where service dependencies evolve rapidly during feature development.
Great insight. Really helpful context. How to implement eBPF deployment safety. Step-by-step implementation guide.
Implementation begins with setting up eBPF development environment and kernel compatibility verification. Teams need Linux kernel version 4.9 or higher with eBPF support enabled. Install essential tools including libdpf, BPP tool, and Clang compiler for eBPF program compilation. Verify eBPF capabilities using BBF tool feature probe command to ensure all required features are available. Set up development containers or virtual machines with appropriate kernel configurations for testing eBPF programs before production deployment. Configure eBPF programs to monitor specific deployment events and service communication patterns. Create custom trace points for deployment tooling that capture service startup, dependency resolution, and inter-service communication events. Implement eBPF maps to store dependency metadata and maintain real-time dependency graphs. Set up user space programs to process eBPF data and perform circular dependency analysis using graph algorithms like depth-first search with cycle detection. Integrate the eBPF monitoring system with existing CI/CD pipelines and deployment orchestration tools. Configure deployment scripts to load eBPF programs before service startup and unload them after successful deployment completion. Implement alerting mechanisms that trigger when circular dependencies are detected, including integration with existing monitoring and incident management systems. Test the system thoroughly in staging environments with known circular dependency scenarios to validate detection accuracy and response times. Install eBPF development tools, litppf, ppf tool, Clang compiler, and verify kernel compatibility 4.9+. Create custom eBPF programs with trace points for deployment events and service communication monitoring. Implement eBPF maps for dependency metadata storage and real-time graph construction algorithms. Integrate with CI/CD pipelines through deployment script modifications and automated eBPF program lifecycle management. Configure alerting systems for circular dependency detection with incident management tool integration.
That's a very interesting point. Tell us about competitive context, how eBPF changes deployment safety landscape.
Traditional deployment safety tools like Helm dependency checks, Terraform plan validation, and static analysis tools operate at the configuration level but miss runtime circular dependencies. GitHub's eBPF approach provides kernel-level visibility that captures actual service behavior during deployment, offering superior detection capabilities compared to configuration-based solutions. Tools like Istio Service Mesh provide some dependency visibility but lack the deep system-level monitoring that eBPF enables. The real-time nature of eBPF monitoring surpasses batch processing approaches used by most existing dependency management solutions. This eBPF implementation creates significant advantages in detection speed, accuracy, and operational overhead compared to alternatives. Unlike application-level monitoring solutions that require code instrumentation, eBPF operates transparently at the kernel level without modifying application code. The approach provides better performance characteristics than user space monitoring tools while offering more comprehensive coverage than network-based dependency tracking solutions. Integration complexity is lower than full observability platforms while providing more targeted functionality for deployment safety use cases. Current limitations include the requirement for Linux kernel 4.9 plus an eBPF expertise for implementation and maintenance. The solution is platform-specific and doesn't address dependency issues in non-Linux environments or serverless deployment scenarios. Complex eBPF program development requires specialized skills that many teams lack, potentially creating operational dependencies on eBPF experts. The approach may generate false positives in environments with complex service interaction patterns that appear circular but are actually valid. Superior runtime dependency detection compared to static analysis tools like Helm and Terraform validators, kernel-level monitoring provides better visibility than application-level instrumentation or network-based tracking. Real-time detection capabilities surpass batch processing approaches used by traditional dependency management tools, lower integration complexity than full observability platforms, while maintaining targeted deployment safety functionality.
Good analysis. Let's continue. What's next? Future implications for eBPF deployment safety systems?
GitHub's eBPF deployment safety implementation signals broader industry adoption of kernel-level monitoring for DevOps workflows. Expect similar implementations from major cloud providers and platform engineering teams managing large-scale distributed systems. The approach will likely expand beyond circular dependency detection to include performance regression detection, security policy enforcement, and resource utilization optimization during deployments. Integration with service mesh technologies and Kubernetes operators will become standard practice for organizations prioritizing deployment reliability. The eBPF ecosystem will develop more specialized tools for deployment safety, including pre-built programs for common dependency patterns and integration frameworks for popular CI/CD platforms. Expect emergence of eBPF as a service offerings that provide deployment monitoring capabilities without requiring in-house eBPF expertise. Development of higher-level abstractions and domain-specific languages will make eBPF deployment monitoring accessible to broader engineering teams. Long-term implications include fundamental changes in how organizations approach deployment safety and system reliability. eBPF-based approaches will become standard components of platform engineering toolkits, driving demand for eBPF skills and specialized tooling. The success of GitHub's implementation will accelerate adoption of proactive rather than reactive approaches to deployment safety across the industry. Industry-wide adoption of eBPF for deployment monitoring by major cloud providers and platform engineering teams expansion beyond dependency detection to include performance monitoring and security policy enforcement during deployments development of eBPF as a service offerings and higher-level abstractions for broader engineering team accessibility integration with service mesh and Kubernetes operators, becoming standard practice for deployment reliability.
Great analysis. So, what are the key takeaways from all of this?
Implement eBPF programs with kernel trace points to monitor deployment events and detect circular dependencies in real time with sub-millisecond response times. Configure eBPF maps for dependency metadata storage and integrate graph algorithms for automated circular dependency detection during service deployments. Deploy eBPF monitoring systems in environments with 50 plus microservices to achieve 85% reduction in deployment rollback incidents. Integrate eBPF deployment safety with existing CI/CD pipelines through automated program lifecycle management and incident response workflows.
And what market signals should our listeners watch for?
eBPF adoption acceleration. GitHub's production deployment of eBPF for deployment safety validates enterprise readiness of eBPF technology beyond traditional networking and security use cases. This implementation demonstrates eBPF's viability for critical DevOps workflows, likely accelerating adoption among platform engineering teams. The success will drive investment in eBPF tooling and expertise development across the industry, creating new market opportunities for specialized eBPF solutions and consulting services. Proactive deployment safety shift. The industry is shifting from reactive deployment failure management to proactive prevention systems using kernel-level monitoring. GitHub's approach represents a fundamental change in deployment safety philosophy, moving beyond static analysis to runtime behavior monitoring. This trend will drive demand for real-time deployment monitoring solutions and create competitive pressure on traditional deployment tools to integrate similar capabilities or risk obsolescence. Platform engineering maturity. GitHub's sophisticated eBPF implementation signals the maturation of platform engineering practices and the growing complexity of deployment safety requirements. Organizations are investing in advanced monitoring capabilities that require specialized expertise and infrastructure. This trend indicates a market shift toward platform teams as strategic technology differentiators, driving demand for advanced tooling and specialized engineering talent in deployment reliability.
What should developers and operators do with this information?
Deploy eBPF deployment monitoring and staging environments within 30 days for teams managing 20 plus microservices with frequent deployment cycles. Implement kernel-level dependency tracking for production deployments when experiencing more than 5 rollback incidents per month due to dependency issues. Integrate eBPF programs with existing CI/CD pipelines for teams deploying containerized applications multiple times daily in Kubernetes environments. Establish eBPF expertise through training or hiring when managing complex distributed systems requiring real-time deployment safety monitoring.
Thank you for listening to leadai.dev. Stay tuned for our next daily updates in this rapidly emerging market.